So our next speaker is Stéphane Robin from Paris, from the University in Paris, and he's going to talk about detecting abrupt change points using a Bayesian procedure.
Okay, so thank you for the invitation and for the opportunity to participate into the workshop. So this is a joint work with a series of people, but most of all the main contributor is not me, but Loïc Schwaller, who just finished his PhD and is now in Leiden in postdoc. So I decided to start with an example to explain the kind of problem I would like to be able to solve, and the problem is the following. So it's a kind of generic problem. So my problem is in gene expression, but I will have several other examples. So suppose you have data like this. It is yijt is the expression of gene J at time t. And the question you have is how is this gene set organized? That is, what is the graphical model which lies behind the joint expression of all these genes at a given time? So typically you would like to encode this dependency structure into a graphical model, so just a graph where I denote GT. And I denoted GT because my question is about the fact that this graph may be constant a long time or not. So the question is it always the same dependency structure, or are there some changes, and if so, when does it change, and if so, also what kind of changes there are there. So just maybe I thought that maybe the best way was to start with the end. So this is one of my last slides. So this is a kind of these are public data. So you have not that many time points. You have a few tens of time points. Again, you can deal with few tens of variables. So here you just have 11. And the kind of result I would like to be able to provide is this one. So I don't think you can see, but there are colors between these embryo zone here, larva zone, pupa zone, and adult zone. So these are the time region that the biologists know about the development of the fly. And this curve here is a posterior distribution of the curve that gives you the posterior probability that there is a change at this time. So when you read this curve, you feel that it is very likely that you got a change in the structure of the network between of the regulated network at this time, and then maybe something happened there, and maybe something happened there. And you also have a dotted curve, but I will explain it later. And the second thing I would like to be able to do is for each period that I can get separated by this change point, to give you an inference about the network, which is for each possible edge, a probability that this edge actually is in the network or not. So that's the kind of thing I would like to be able to do, to give you a posterior distribution of the location of any change point, if any, and the posterior probability for each edge to be there in a given region. So you can, I know at least two other problems where you have exactly the same question, which is in ecology. We have species abundance a long time, and you would like to know if the interaction network between all the species is constant a long time. So we have a collaboration at this time about bacterial species on the leaf of grape wine, depending on when the plant develops. So it seems that the ecological system varies a long time along with the growth of the plant. And another one, but I hardly dare to introduce this one after your talk. But basically it's the same. That is, you have an activity of brain region. So I guess every single word in this sentence is too naive. But again, I would like to know if this connectivity, and I know there is no change in the physical connectivity, but just in the exchange of information, may change depending on, for example, whenever people are submitted to a given task, and the task change a long time, so you would like to see this. Okay? Yeah?
I'm curious how these species are being chosen. Are they being chosen at random from a population, or
so it's a bit the same situation as what Susan explained. In many situations, people have their own favorite species, so they know how to identify them because it's the few tens of bacterial species they know a lot. For example, they can be responsible for the development of a disease. So you want to have this one and all the species that you know that are potentially associated with this one. So we are given with a list of species, and it's not that large. Okay. So from a from a statistical point of view, so you can't see there are things written there. Okay. From a statistical point of view, the problem is that I would like to do Bayesian inference because I want to give a measure of uncertainty. So that I don't want to give you a change point. I want to give you a posterior distribution for this change point, and I don't want to tell you this edge is present. I want to give you a probability for this edge to be present. And the difficulty here will be that if you think a bit of this kind of models, I will have to deal with discrete parameters. So what do I mean by discrete parameters? Just suppose, just consider the simple case where you have a series of Gaussian data. So you will typically need to have a mean, variance, correlation, things like that to explain how the different variates vary. So their means, their correlation, etc. But then you will have also to say something about the change point. So there is a change point there or not. So mean, variance, correlations, all these guys are continuous parameters, whereas change point location, graphs, that is, an edge is there or it's not there, are discrete. And one typical quantity you need to compute whenever you do Bayesian inference is, for example, the marginal probability of the data. And when you have this kind of situation, you need to integrate out over all the continuous parameter, and you need to sum up over all the possible value of the discrete parameter. So that's my big deal today, because at some point, whenever the space of the discrete parameter is large, computing this sum may be an issue. Okay, and the thing is that for the two problems I'm mentioning, that is change point detection and network inference, you can find some algebraic shortcuts so that you can actually compute this sum. So that's mainly the topic of my talk today. So again, suppose that so t around here is the size is the set of for the discrete parameter. If t is small, you don't really have to care about this sum. For example, when you do model selection, you ask whether there is 1 change point, 2 change point, up to 10 change point. You can try the 10 and do the sum, and you're glad. So it's not a big deal. But sometimes the size of t grows super exponentially with the number of data or the number of variables, and you can't do that anymore. So I will have 3 examples. First, I will come back to change point detection without network. Then I will go to network without change point, and then I will go to both. Okay. Which kind of classical outline. So for change point detection, the classical model is the following. So you have your data like that, and then you have changes. Changes means that the time is split into segments, region. Here I've plotted 1, 2, 3, 4, 5. But let's say this is the first one, this is the last one, and this is any of it. But because I'm doing Bayesian inference, in addition to that, I have to draw one parameter which will rule the data in segment 1, one parameter which will rule the data in segment R, one parameter which will rule the data in the last segment. Okay? All along this talk, I will make the same assumption, which is that whenever I need to integrate out about this parameter, I can do that easily. So if ever you took your favorite distribution in the exponential family, you can do Gaussian inverse gamma prior. You can use gamma prior if you have Poisson, etc. So there are plenty of situations where you can compute this integral there with not too much effort, meaning that at the end of the day, whenever you want to compute the joint distribution of the distribution of the data given a given segmentation, you just have to compute something like a product of all the segments of the segmentation. So the segment of the segmentation, this is the first segment, then you have several others, this is another one, several others, and this is the last one.
Is K given to you?
K is a part of it, but again, it's not a big deal because I won't explore, K won't grow, the number of possible value for K will not grow super exponentially with the number of data. So I can try with K 1, 2, 3, 4, 5, and then do the thing I do. So of course, K is a parameter, but most of the distribution I get, so there should be a given K there, but if you give me T, you give me K, because you give me the number of segments. Okay. So the key thing is that the distribution of the data is just a product of all the segments, and after integration of all the parameter, which is usually not too hard to do, at least for simple models. So if you want to write things here properly, if you notice that here what I will do is that I assume that the parameter in this first segment are independent from the parameter from this segment and independent from the last segment. So I assume that the parameter are drawn independently in each segment, and then I assume that the data are independent from one segment to another. And the last assumption I do is that the prior distribution for the segmentation is also something that which I could write like a product. There should be a proportional to here, because if you give me this coefficient there, I will need the normalizing constant to make this a distribution.
So the network between different
So at this time, I have no, I'm in stage 1, I have no network. I will have network in stage 2, in second part. So I have no network now.
What is independent between the segments?
The data from the first segment, so the data from time 1 to time 10 are independent from the data from time 11 to time 20. Okay, so I may deal with dependence within a segment, but not with dependence from one segment to another.
So are you assuming conditional independence, given the parameters?
Yes, no, well, it's given the parameter, most of the time here I will assume a conditional independence, but it's not necessary. I could have, the critical assumption is this one. I want the data to be independent, even unconditionally on the parameter, from one segment to another. Okay, this is a critical assumption. So this is why all this distribution here all factorize along the segment of the segmentation. So it's always a product.
Is it a sensible assumption?
This one? Which one?
That you have independence between the...
Well, in plenty of examples I know, you can do that, because if you just have to deal, for example, with noise, that is just you have a mean value in one period, then you go to another mean value, and then to another mean value, and all the variability is about measurement noise. You may assume that at it, in plenty of applications, time is just a name. For example, I work a lot in genomics, and time is just a position along the genome. So you may imagine that you have a measure there, and you take the two measures independently from. Okay, so if you do the assumption for the distribution, what you will see is that the key quantity I will have to deal with typically is the marginal distribution, or the distribution of the data just given the number of segments, as this form, which is the sum of all possible segmentation of a product of all segments. So you have a term which depends on any segment. So a segment is just defined by 2 time points, and it's all the data in between and all the parameters that will be associated with, and all the parameters there, which tells me something about the prior distribution of the segmentation. But I have to deal with this kind of sum of product. And the thing is that, of course, I can't deal with this sum because it goes exponentially fast with the number of data in k. And if, for example, you want to say something probably more interesting, like the posterior distribution of the change point, that is the probability that there is a change point at this location there, you will need to consider all the possible segmentation of the data up to t, and then all the possible way to segment the data from t to the end. And again, you have this sum product thing. Okay. So the thing is that you can manage this sum, and it's just due to some simple algebra. If you take an upper triangular matrix with 0 on the diagonal, whenever you take a to the square, for example, and if you develop the last term, that is the last first row, last column, what you have is just f11 times f2n, or f1i up times fi plus 1n, etc. So you visit all the possible way to split the interval 1n with one intermediate point, which is I. So when you do that, when you take your matrix to the square, you visit all the possible way of segmenting the interval 1n in 2 pieces. And if ever you take this to the cube, again, the kind of the element of the product you have, because it's upper triangular with 0 on the diagonal, the kind of the terms you have is f1i, then i plus 1 to j, then j plus a plus 1 to n. That is the 3 term corresponding to 3 successive segments. So when you do that, you're summing over all possible segmentation into 3 pieces. So the generic tool for that is to say that whenever you take this matrix, which is upper triangular, whenever you take it to the k, you've visited all the possible segmentation of your data set into k segment. And the price is just taking your matrix to the power which interested you. So it has nothing to do with the total number of segments. So you can use that to compute plenty of things. Actually, there was a paper by Paul Funhead some years ago which was using a similar idea, although not exactly the same for online segmentation. So there is a package doing that, by the way. Okay, so if I go back to my first example, so this is exactly the example I showed you, but there is no network there. So I'm just saying at each time, I suppose that there is a covariance matrix between my p genes, and I just assume that the distribution, that is just the mean, and the covariance matrix may change from time to time, and you end up with this dotted line there. Okay, so that is, you find plenty of change points if you do that, and some of them are not very uncertain, but you find plenty of change points. So you can apply that directly, but here you have no network assumption at all. You say nothing. People name that the saturated graphical model. You assume that everybody can depend on everybody. So it's just a change point detection in a multivariate series with just multivariate Gaussian distribution. So you can do that, and it's very fast because the number of data it's not that large. So you can do that, but again, it's not very satisfying, and one possible reason for which it's not very satisfying is that you say nothing about the structure of this sigma here. You don't say, you allow any gene to depend on any gene, and you don't want that. So that's what you need, the second ingredient, which is to do network inference. And to do network inference, I will borrow the framework of graphical models, but I think everybody knows that perfectly well, which is to say that a joint distribution is faithful to a graph if it can be factorized along the cliques of the graph, the maximal cliques of the graph. So basically, when you draw this graph, you have a picture of the conditional independencies between the variables. So this is a kind of tutorial. If ever the graph is like this, it means that the joint distribution can be factorized like that, and it tells me that this guy is independent from this one given this one. So y6 is independent from y5 given y2, and from any other node which would be on the other side of y2 with respect to y6. But I think that this is clear for everybody. So basically, what the network inference problem is, I give you an IID set, an IID sample from P, and you would like to infer G. But basically, that's exactly the same problem as Eric was speaking about yesterday, if I remember well. So I'm going to make an assumption to be able to. So again, when you do that, if you want to do that in a Bayesian way, at some point you will need to integrate out of all possible graphs. So that's what I don't want to do, at least not by hand. And now I'm doing a quite stringent assumption. I'm going to assume that the graph is not any graph. I'm going to force the graph to be a spanning tree. Okay, meaning that this graph is not allowed in my model, but this one is allowed, this one is allowed as well, and this one is allowed as well. So in some sense, the idea is that at some point I will average over all possible trees. So you can see this graph. So the true graph would be with a full line there, but you can see this graph as a kind of mixture of the three trees that I just drawn, these three ones. Okay. So you said that instead of having the joint distribution that would be faithful to this graph, I will use a mixture of these three graphs which are there. Okay. So this assumption is consistent with the fact that the graph is sparse. That is the good news. The bad news is that obviously it's very unlikely that the true graph is a tree. But as I was showing you, will only provide information about, for example, presence or absence or edges. Nothing more complex. For example, if you ask me, is there a triangle there? I can tell you the answer now. The answer is no, because there is never any triangle in the graph. Okay. So is there a triangle there? No. But what you will see that at the end of the day, when you get posterior probability for each edge, for example, you get a posterior probability for each edge and then you threshold, at the end of the day, you will end up with something which is not a tree at all. Okay. And by the way, you can have a triangle once you've thresholded. So clearly it's an assumption, but it's a way to reduce the space of graph I want to visit. And now again, I want to do Bayesian inference, so I have to be a bit careful. So I have to say something about the prior distribution of the parameter. So if I want to say something about the prior parameter I want to put here in this kind of graph, I will have a parameter which tells me something about a parameter that tells me something about the relation between y1 and y3, the same between y2 and y3, and also marginal parameter just for y1, y2, and y3. And the thing is that if I want to be able to use the kind of algebraic tool I'm going to use, I need this prior distribution to factorize along the tree in the same way as the distribution of the data factorizes along the tree. So this is not completely trivial, because I want my prior distribution to factorize along the tree, and because I want to average over all trees, I want this to be true for any tree. And you can't do, there are not that many different cases. So this is very, very well studied in an old paper by David and Lorison, where they started to make a list of situations where you can do that. And basically, it's only the situation that you know pretty well. So it's either the multinomial Dirichlet and the normal Wishart. And it's because these distributions have very nice marginalization properties. Whenever you compute the marginal, it goes very well. You have another example which is quite obvious, which is whenever you use copulas. Because whenever you use copula, basically, the marginal distributions are fixed to uniform or something. So you have no theta 1, theta 3, theta 2. So you don't have to care about the fact that, for example, theta 3, theta 1 here has to be consistent with both theta 1, 3 and with theta 1, 2. because there is no theta 1. So the big thing is that whenever you marginalize, whenever you integrate out with a theta, with respect to theta, this guy has to be consistent. The integration with respect to this guy has to be consistent with the integration with respect to these two guys there. And there are not that many distributions that allow to do that. So that basically, we wrote a paper on that, and we have a hard time to make it published, because basically the idea of averaging over tree is not new, so people already did that. But to try to set properly the framework for Bayesian inference is not that trivial. You have to go along all this to understand what you do and when you can do it. So if ever you want to do Bayesian inference, so now, as you see, I have no theta anymore, so I assume that I have done the integration, but I can do the integration with respect to any tree just in this list. Maybe there are some other case, but it's not any distribution. So now if you're able to do this integration, you face a similar situation where if you compute the distribution of the data, now T is a tree, so it's my graph, I have a product over all the marginal, and then I have a product over all the edges of my tree. Okay, and at the end of the day, so again, the quantity I will need is something like product over all the edges of my tree. So if I take a prior over the tree which has the same shape, which is proportional to a product over all the edges of my tree, the kind of quantity I would like to compute are quantity like that. That is the sum over all possible spanning trees of product over all the edges of my tree. So if you remember, when I was doing segmentation, I was doing something like summing over all segmentation of a product of term along each segment. Now I want to have a sum over all possible trees of a product over each edge of my tree. Okay, so if you want to compute the marginal distribution, you have this shape here. If you want to compute the posterior probability for one edge to be absent, you have more or less the same thing, except that you want to kill one edge, but it's not very hard to kill one edge. You put this to 0 and that's it. So typically you want to compute this kind of thing, and you don't want to make a sum over all this, because this is super exponential. Okay, this is p to the p, so it's too large. Okay, and the thing is that there is a magic theorem, which is named the matrix 3 theorem, which tells you that if ever you have a matrix like that, you compute its Laplacian, then you take any minor of this matrix, and any minor of all the minor are equal, and they're all equal exactly to the quantity you want. That is the sum of all possible spanning tree of a product of all these terms. So in some sense, the tool was already existing. By the way, I use this reference, but I'm quite sure this result is even older. Maybe it traces back to the 19th century. So my question was why people in the 19th century were caring about spanning tree. But anyway, what was the problem? Okay, so again, you can compute exactly the same sum at the cost of computing a determinant. Okay, so you can integrate over all possible trees. And so as I was saying, this has already been used before. There is a paper by Kirchner and also a paper by Mela and Yakola years ago. But again, you have to set it down properly into the proper Bayesian framework. One thing that you may, so you can compute almost anything you want. So typically you would like to be able to compute the posterior probability for one edge to be present, that is to belong to the tree. It's always the same when you do Bayesian inference. The posterior probability is strongly related to the prior probability. So if you take a uniform distribution over the tree, and if you have many variables, the prior probability of any edge would be very, very low. So you may change the prior probability edge by edge to be able to for example, set a prior probability of 1/2 to any edge before to make any decision. Because the prior probability for any edge, if you take a uniform, is not 1/2. It's something like 1/p. So you can adapt a bit this. You can do a change of measure to change this. Okay, but again, so you will need to do that for each for each possible edge. So I just finished by so you have a determinant to compute there, so it's p to the cube, and you have p square edge, so you will end up with p to the 5. But again, there is an algebraic trick which tells you how to compute this for any edge, all the edges at the same time, for p to the 3. Yes?
If I understand correctly, the kind of magic on the previous slide, it does oblige you to use uniform prior.
Sorry? No, it's not only for uniform prior. As long as my prior is like that, like that. As long as it's factorized this again. So if you have prior information about the fact that this one edge is more likely to be there than another, I can encode it like that. But it's only about product over edges. If you have an information about pairs of edges, I don't know what to do with it. Okay, so the only prior, so I have flexibility here, but only under this shape. Okay, so if I want to summarize, what you are able to do is for any tree you can compute its posterior probability for given the data. So this is for this one tree, another tree. So I go along all the possible tree, and what you end up with is a posterior probability for each edge to be there after integration, and you can do that using the matrix tree theorem. And usually what we do is that you just threshold this at, let's say, 1/2, because it's a probability, and whenever I have no idea threshold at 1/2, but you may threshold wherever you want. And what I wanted to emphasize that at the end of the day, this is not a tree. This is not spanning, because this guy is isolated, and this is not a tree because I have a circle there. So I may end up with an infinite network which is not a tree, although I integrated only over all the trees. Okay, so just a few simulations to show that basically if you do network inference, if the true network is a tree, life is not that bad. If you take an Erdős-Rényi network but with the same density as a tree, again it works not too bad. And of course, if you go further away, the ROC curves are not that good. But I don't know if you ever had you probably already had plenty of talks about network structure inference, and the ROC curves are never like that in real life. Okay, many times they look like that. It's a difficult problem. Okay, and you may see these little dots here, which would be which would correspond to the result we would have if we were doing maximum likelihood. Okay, so here we have a ROC curve because we have a probability for each edge. So of course, one question is how bad is it to assume that it is a tree? So what we did is that we compare with another Bayesian inference, which did MC sampling in the set of DAGs, which is a larger set of graph, which is the one typically people want to refer to. So forget about the blue result here. In some sense, there are size results. The big thing is that the light gray, I never remember. The light gray is the one when you average over trees, and the dark gray is when you sample over DAGs. And the main result is that it's exactly the same. Okay, so our purpose was not to beat them. Our purpose was to show if we were worse than them. And basically, the result is the same. That is, we have the same AUC or the same precision recall, etc. The only difference is there. This is the time it takes. Okay, this is 2,000 seconds. This is 2 seconds, just because you integrate out with just one determinant. Okay, so this is an example with flow. How do you flow cytometry? Flow, yes, I'm correct. Flow cytometry, yeah. Okay. Well, there was a kind of ground truth, but it's always the same in biology. The ground truth of the network is the one people know at one time. So this is what the ground truth on Monday. And okay, this is the infinite network, and basically we recover plenty of things. But of course, thresholding matters. So the threshold that you put on your network is still to be done before you do something. And if you do, for example, maximum likelihood, you end up with this most likely tree, and this would be the second most likely tree. Okay, so now I would like to do both, and I hope I won't be late. So my model is this one now. Okay, so I have, let's say, 7, am I 7 or almost 10? Well, 8. Okay, sorry, 8 variables, and now I have a change point. So until now, the graphical model is this one, and now there is a change, and now it's another one, another graphical model. But if you look carefully, you see that all my graphical models are trees. Okay, so I will limit to trees. So the example are the one I already mentioned. So if I want to be more specific about the model, the first layer of the model is the number of segments I have. Then you draw the segmentation in the set of segmentation into k pieces, and I ask my prior distribution for the segmentation to factorize along segments. Then for each segment, I have to draw independently a tree, and so each tree is drawn independently in each segment. And again, I should have written that each prior is also a product of its own age. Then I have to draw my parameter, and again, I need to know this prior has to be consistent with the any age. So again, I only have a limited number of distribution for which this is possible, and then the data are drawn independently given all the rest. So typically I would not compute always the same. The distribution of the data, let's say, given the number of segments, so I would need to sum over all possible segmentation and to sum over all possible sets of 3, 1 per segment. And again, I have this sum of product. Okay, but we know how to compute this sum. You take a matrix, you take it to some exponent. We know how to compute to this sum. We take the determinant of. We use the matrix tree, so we should be able to do the same, to do this, and basically that's what you do. So if you do that in a naive way, this is the order of magnitude of the number of segmentation. This is the number of magnitude of the number of trees. So you will end up with this kind of complexity that nobody wants to have to deal with, of course. And if you combine the two, the first complexity was kn squared, the second is p cubed. So at the end of the day, you have this kind of complexity. From my experiment, k is never larger than p cubed. So k would be the number of segments, and p cubed is the number of nodes to the cube. So usually the complexity we have to deal with is p cubed n squared, which is large. So you can't do that for thousands of nodes and millions of data points. Okay, you can do that for few tens of nodes and few hundred. I will mention the limitation for this approach. So now, once you do that, you can compute a series of probability of interest. For example, you can compute the posterior probability that there is a change point at a given time. You can compute the probability for a given edge to be present at a given time. You can compute the probability for a given edge to be present all the time, to stay there all along. You can compute the posterior distribution of the segment, etc. And if you think a bit of the problem, you see that as soon as you know how to do a change point detection in network, a sub problem is to do network comparison, because you can easily compute the posterior probability for two graphical models to be the same given the two data sets. It's just a sub problem of the preceding one. Okay, so just one thing so if you remember, at some point I showed you this plot where you had continuous line and dotted line. Continuous line where I'm not there. Okay, so this one. Okay, sorry. So this is the one you get. So the dotted line was when you did not assume anything about the hidden network. It was a saturated model. Okay, we had plenty of changes. If you force the hidden network to be a mixture of trees, you have much less change point, and basically you find the change point almost where you expect them. That is, you find this between embryo and larva, between larva and pupa, and here you find it just in the middle of the embryo stage. And actually, we are not the first to analyze this data, and everybody finds a change point there. So probably there is something which within the embryo file there is a kind of gene rewiring. So there is a gain to use the tree approximation, because it strongly reduces the space of the graphical model you visit. And at the end of the day, within each of this region, you can compute the posterior distribution, the posterior probability for each stage to be present in each region. So I have another example, but so I just to show that it's an experiment where people are. So it's a kind of, this is a typical neuroscience experiment where the scientists are just torturers. So people were told that they will have to make a speech in front of something like 100 people. So and now, at this time they were given with the subject of the topic. So you had 2 minutes. Let's start to think of what you're going to say to these guys. And now at this point they were told, finally you won't do it. Okay, and so is it? So no, they were told you will have to say something. Now I give you the subject, and at this time I tell you won't do it. Okay, so you get a kind of release. So you're a bit angry, but so these are the change point detection we find if you do that patient by patient. And so you see that the change points are not that obvious when you work patient by patient. But when you take all the patients all together, it's much more neat. You find posterior distribution, posterior location for the change points that are much more precise. Okay, I just wanted to mention that. And you have because all the patients were submitted to exactly the same experiment. Which it's a kind of obvious statistical remark, but it's worth to grab them all together. Okay, so a few points to discuss. So my point was that in some situation, whenever you have a model with this kind of a bit complex situation, you can be tempted either to do a sampling, MCMC or something like that, or to do approximation, variational Bayes, etc. Sometimes it's good to be hard-headed, because you still can do the exact calculation, just because in this case it's just because you have the nice algebraic tool. The good thing is that you don't have to care about the fact that your MCMC has been convergent to its stationary distribution, because there is no such thing like an MCMC there. So this is a good point. And the thing is that I just showed you two examples, change point detection and tree structure network inference, for which I have an algebraic tool which does the job. The question is, I have no idea of other similar situations. I just just want to make one remark, which is that, for example, when you do a change point detection, we just see that taking a matrix to a power allows you to make Bayesian inference because you can integrate out of all possible segmentation. If you wanted to do maximum likelihood, this problem would be a shortest path problem, and you can solve it by dynamic programming. For tree structure network, what we saw is that whenever you want to do a tree structure network inference in a Bayesian setting, you can use the mass produced theorem to do this integration. If you are doing maximum likelihood, it would be a maximum spanning tree problem. And again, you know how to solve that, okay? And in the two cases, we know the reasons. There is a kind of parallel in terms of algebra. On the left, it's a sum product problem. On the right, it's a max sum problem. My question is, do you have any other idea of problem where again, similar, do you have any other idea of set T there for which this kind of sum or integral or whatever you want or maximization is easy to do? Because if so, it would broaden the set of models with discrete parameters that we can tackle in an exact way. These are the only two I know. And again, here you don't have to, in terms of Bayesian inference, here you're almost free to do whatever you want because the parameters are naturally independent from one segment to another. Here you have to be much more careful because of this marginalization property that you need to have in your prior. Okay, so what could we do first? Well, first, I assume that there is no dependence between the data from one to another. Actually, I can have dependency within a segment. It's no big deal. You can have, as long as you integrate out, and this is again a tree, so you could deal with this kind of dependency, but I will not allow dependency from one segment to another, otherwise I lose everything. There is something which we should care about, at least whenever we would have to deal with very large data set, which is how the prior goes diffuse whenever you increase the number of data, because you have a huge the dimension of the set where the discrete parameter lives grows super exponentially, and if you let the prior do whatever it wants, for example, if it's uniform, at some point it's very likely that your posterior will be very diffuse as well. So probably you need to tune that a bit depending on the set of the data. In terms of scaling, the bad news for us was that in terms of scaling, the complexity is p square and p cube n square. So in some sense, when you know that, you know everything. But the bad surprise was about numerical issue, was just about the fact that we compute exactly all the probabilities. So at some point, you need to make a sum of plenty of terms that are very, very different order of magnitude. And it's not a matter of that. It's not a problem that computing this takes time. It's not that long, but you go to very bad number because it's not a matter of condition. Just summing a large number of numbers, which very, very different order of magnitude. And at the end of the day, we had a big trouble. So for large data set, at this time, we do something completely stupid. We do tempering, the kind of tempering Bayesian people use. That is, you put a power alpha to your log likelihood. Alpha is smaller than 1, which means that the posterior credibility interval you give are larger than they should be. So we provide people with results that are less precise than they should be just because of that. So we face this kind of problem before to face computational time problem, which is a pity. And I think it's a bad thing because in some sense, maybe it's a limitation in a general limitation for exact Bayesian inference, because at some point it means that you have all this very nice algebra, but you can't compute your quantity because of this different order of magnitude. Okay, and so I'm good.
When you have multiple subjects, then would it be sensible to actually incorporate the mixed effect models over this variation of the segment length? The point.
We didn't. It would make sense for sure. But the second question is, am I able to fit it into this? And the answer, I never thought of it. So, well, if the tree is the same for all patients, but then you have fluctuations for the parameters from one patient to another, I think you can adapt that, because it's just a matter of integrating along each edge. Instead of doing the integration for all the patients at once, you do one integration per patient, but you can do that as well. So I would say yes.
to some extent, your explanation of why you actually want to focus on trees makes some, kind of intuitive sense. You kind of average out over all kinds of trees, and you might get a kind of the underlying network, basically. But from the point of view of a graphical model, it's actually still quite surprising, because obviously the absence of one edge may actually, lead you to believe that, certain other edges may be absent as well, or maybe actually induce the presence of other edges. So have you got any kind of insight why just dropping some edges in a graphical model somehow still kind of preserves the kind of probabilistic closeness apparently between the true graphical model and the approximating tree?
So I have no theoretical answer at all. I have one intuitive answer, which is that whenever you do what you say, still you integrate out over all possible ways, all possible tree structure for the rest of the network. That means you will consider all possible rewiring of the edges at some point. So that's what I hope. And the other argument I have is that on simulation, when compared to DAG, so sampling in the space of DAG, the performance is the same. So I fully agree it's a bit weak, but that's all I have it now.
One question, I saw in the examples P was pretty small, and you said that
I can't really.
P, the quantity P
Yes.
was pretty small in your examples. I mean, have you this?
Yes, we pushed it a few tens, and for n, few tens or a small number of hundreds, but not more. It's because you have this. You consider it's really because of this numerical issue. At some point, you will deal with something which is the exponential of n times p, because you will have a kind of likelihood which has.
How much will you lose if you just look at the last line? If you don't, and I've seen cases in which people just drop. I've done it myself. You just drop. If you have a sum of probabilities, if you sort of if you're able to rank order them or know which ones are small, you might drop 90%.
The thing is that you don't see the element of your sum, because you compute your sum either by computing a determinant or by taking a matrix to a power. So it's not, for example, the standard trick to avoid this kind of thing is to sort the term of the sum starting from the smaller to the other, but we never see the term of the sum. So probably one thing which would be possible would be to recode the formula of a determinant in a clever way. We didn't go into that because we're much too lazy to. But that would be probably something to do.
So maybe a naive question. So suppose that you only have a single change point to make life simple. Don't you need the identifiability condition of how big the change is in order to be able to detect it in the first place? Otherwise, what are you computing?
I mean, in terms of whenever the jump is small, what is very, very likely is that the posterior distribution of the number of change points will be a Dirac on 1. It's saying that there is only one segment. So what in a Bayesian setting, this question is not exactly stated in that way, because you will get a posterior distribution which tells you I don't think there is any change. That's it. So the posterior distribution of the number of segments will be a Dirac on 1.
So then do you have any information of if there is a change, at what rate the posterior concentrates?
No, we didn't do that. No, that's probably something like that, which is one of a typical idea where Loic was thinking to go on. We didn't do that. We didn't go at all on the frequency properties, for example, of this posterior distribution. Our purpose was just to compute this distribution.
You said you have to be careful with how you set your prior, because if you just use the uniform, then it influences the posterior far too much. So I don't know if you could expand on that. So do you want to make that each edge has a really small probability in the prior?
So to me, this point is clear whenever you speak about change point detection, because if you really take it uniform, the vast majority of segments will be very, very, very small segments. So your prior will be completely diffused. So probably using the prior on the segmentation, you can force to put some prior favorable information for reasonably long segments, and you can do that easily because I don't want to go back too fast, but I'm going to do it anyway. And this is not hard to do, because when you put your prior on the segmentation, which is this guy here, you can typically take this prior there, which depends on the length of the segment to some power. So depending on the alpha you put there, you will favor small segment or long segment. So in this case, it's easy, and you see how to control the diffusion of the prior. As for the trees, it's much less clear to me because it's much more symmetric. So I don't really see why I should. Probably I would really need to use true prior information telling me that this edge is much more likely to exist than this one.
Okay, so let's
Thank you.